For a long time, the W boson looked like one of the finished numbers in physics. Not because it was easy, but because the standard model ties it down from multiple directions. Measure a few other quantities precisely, run the electroweak machinery, and the W mass is not supposed to have much freedom left. It should land in a narrow window. Every serious experiment should converge on the same answer. And then one measurement came back too heavy. Not by a tiny nudge that disappears in the noise, by an amount large enough to make people ask a dangerous question in particle physics. Is this a real crack in the standard model, or did a world-class detector fool the field? Here is the whole problem in one sentence. The W boson mass is about 80 giga-electron-volts. Most measurements cluster around about 80.36 to 80.38 giga-electron-volts. But one ultra-precise result reported about 80.4335 giga-electron-volts, with an uncertainty of only about 0.0094 giga-electron-volts. That difference is not a rounding error. It is tens of mega-electron-volts. In this business, tens of mega-electron-volts is an argument. So what is the W boson, and why does its mass matter this much? The W boson is the carrier of the weak force. It is what makes beta decay possible. It is why the sun can shine the way it does. It is a cornerstone of how particles change identity. But in the standard model, the W boson mass is also a pressure gauge. It feels the influence of other heavy particles through quantum loops, including the top quark and the Higgs. If unknown heavy particles exist, they can subtly tug on the W mass as well, like a hidden weight on a calibrated scale. That is why the W mass is a high-stakes number. It is not just a measurement. It is a consistency check on the entire framework. And that is what makes this story so brutal. The disagreement is not about some exotic, hard-to-define concept. It is about a single number that should not be negotiable. But before the drama, it helps to understand why measuring the W mass at a collider is so tricky that two excellent experiments can end up in tension. At a hadron collider, the W boson is usually seen through its decay into a charged lepton and a neutrino. The charged lepton is visible. The neutrino is not. It escapes the detector. So the W mass cannot be reconstructed directly the way it can in a clean textbook diagram. Instead, experiments infer it from the shapes of distributions in the plane transverse to the beam, where the initial momentum is known to be close to zero on average. There are three key observables. The first is the charged lepton's transverse momentum. The second is the missing transverse momentum, inferred from everything else in the event. And the third is the transverse mass, built from the lepton and the missing momentum. Now comes the catch. The W mass is not read off like a label. It is extracted by comparing real data to a huge set of simulated templates. Those templates depend on many inputs: how the detector measures momenta, how the W is produced, how the proton's internal quarks and gluons share momentum, how radiation shifts the lepton's momentum, how the hadronic recoil is modeled, how pileup and soft activity behave, and how the calibration is anchored. A W mass measurement is not one measurement. It is an entire chain of calibrations, corrections, and modeling choices that must all be consistent at the level of a few parts in 10,000. So when someone reports a W mass with a precision below 10 mega-electron-volts, the immediate reaction is two-sided. On one hand, that is a masterpiece. On the other hand, it raises an uncomfortable thought. When the uncertainty gets that small, anything slightly mismodeled can dominate the result. That is why this one heavy number hit so hard. The measurement that lit the fuse came from the CDF2 detector at Fermilab's Tevatron, using the full Run2 dataset. The reported value was about 80.4335 giga-electron-volts, with that striking 9.4 mega-electron-volt uncertainty. That result is higher than the cluster of other measurements, and because the quoted uncertainty is so small, the tension becomes statistically severe. But the story does not end with CDF versus the world, because other measurements exist, and they matter. At the Large Hadron Collider, measuring the W mass is even more challenging in some ways, because the environment is busier. The collision rate is higher. The hadronic recoil modeling is harder. The proton-proton initial state is different from proton-antiproton. And the W tends to carry different kinematic features. Yet LHC experiments have produced measurements that land much closer to the standard model expectation and to the older global averages. For example, one ATLAS measurement landed around 80.370 giga-electron-volts, with an uncertainty around 19 megavolts, and the later improved ATLAS reanalysis reported around 80.360 giga-electron-volts, with an uncertainty around 16 megavolts. LHCb has also weighed in with a result around 80.354 gigavolts, with a larger uncertainty, but still nowhere near the CDF central value. And when the community builds a world average while accounting for correlations in theory inputs, the combined value without the CDF Run 2 result sits around 80.369 giga-electron-volts, with an uncertainty around 13 megavolts. That is the shape of the battlefield. One extremely precise result at about 80.4335 giga-electron-volts. A set of other results clustering around 80.35 to 80.37 giga-electron-volts. Two camps that cannot both be right at the level of the quoted uncertainties. So what does that mean? It means the W boson has become a test of something deeper than a single particle. Either there is new physics pulling on the electroweak sector strongly enough to shift the W mass by this amount, while still respecting many other precision constraints, or there is a systematic effect somewhere in the measurement chain that has not been fully captured, and it happens to push the extracted value high. Both possibilities are serious, but they are not equally easy. New physics is tempting because it is dramatic, but the standard model is not a single equation you can break in isolation. It is a web. A shift in the W mass typically echoes into other precision observables. It affects the global electroweak fit. It must coexist with the measured Z mass, the measured top mass, Higgs properties, and a long list of collider constraints. So if the W really is heavier in nature, the next question becomes, what kind of new particle or interaction could do that, and why has it not shown up elsewhere? That is why many physicists start from the opposite direction. Assume the standard model is fine. Ask what would have to go wrong to pull the extracted W mass upward by tens of mega-electron volts. And there are several suspects that are boring, but powerful. First, detector calibration. The W mass at hadron colliders depends intensely on how accurately the detector measures the charged lepton momentum, and how well that calibration is transported from control samples into the W sample. Experiments calibrate with Z bosons, because Z decays into two leptons and can be reconstructed cleanly. They calibrate with J psi and upsilon resonances as well. They build a momentum scale and test it relentlessly. Second, parton distribution functions, or PDFs. A proton is not a rigid object. It is a probability cloud of quarks and gluons. The momentum carried by those constituents affects the production kinematics of the W. And because the W mass is inferred from distributions, any shift in the predicted shapes can bias the extracted mass. PDF uncertainties are not just theory noise. They are a direct lever on the result. Third, QED and electroweak radiation. The charged lepton can radiate photons. The event can include extra radiation that changes the measured lepton momentum distribution. The modeling of these effects must be precise and consistent. Fourth, hadronic recoil modeling. The neutrino is inferred through missing transverse momentum. That missing momentum depends on how well everything else in the event is measured. The recoil is messy. It depends on soft QCD. It depends on pileup. It depends on detector response to low energy activity. This is one of the most fragile pieces of the entire method because it is both essential and difficult. Because from the outside, this looks like a clean fight over one number. But from the inside, it is a competition between two different kinds of excellence. One kind of excellence is squeezing uncertainty to the floor. CDF did that. That is why their error bar is so small. The other kind of excellence is ensuring that the last tiny systematic is not pretending to be physics. That is what every cross-check tries to guarantee. And right now, the field is in a strange position. The CDF analysis is not casually dismissed because it is technically impressive and internally consistent. But it also cannot be simply accepted because it would imply a shift that sits in tension with other precision measurements and with other W mass determinations. So what is the status today? The honest answer is that there is no universally accepted resolution. There are working groups that have reevaluated correlations, theory inputs, PDF treatments, and common corrections to compare measurements on equal footing. When all major measurements are combined with these careful treatments, the compatibility becomes uncomfortably low. Remove the CDF run 2 point, and compatibility becomes high. That pattern does not prove CDF is wrong, but it is exactly what you would expect if one measurement is the outlier. So the case is open, not because nobody understands the standard model, but because the measurement is hard enough that it is possible for world-class work to disagree. And that brings up the question that makes this story bigger than the W boson. What would actually settle it? Not debate, not louder arguments. A new measurement with comparable precision using a different detector and a different set of dominant systematics. That is why the next steps matter. Atlas has already revisited its W mass analysis with improved methods and reported a value consistent with the standard model. Other experiments are working toward better control of recoil, PDFs, and calibration. CMS has the statistical power, but the systematic control required is brutal. LHCb offers a different acceptance and different sensitivities. Each one attacks the problem from another angle. If a future measurement lands near 80.433 giga-electron volts with a tight uncertainty, the standard model will be in real trouble. If future measurements continue to cluster near 80.36 to 80.37 giga-electron volts, then the story will likely converge toward a systematic explanation for why that one measurement ran high. Either way, something important is happening, because the W boson mass is not just a number. It is a stress test of whether particle physics can still do what it claims: measure fundamental parameters so precisely that the universe has nowhere to hide. There is one final twist that makes this even more unsettling. The W boson is not new. It has been known for decades. The Standard Model's electroweak sector is one of the most successful structures ever built in science. So if a mature, well-studied particle can still produce a measurement conflict like this, it sends a message. Not that physics is broken, but that the line between new physics and unknown systematics is not philosophical. It is experimental. It is fought in calibration curves, PDF fits, recoil models, and tiny corrections that most people never see. And the next decisive result may not come from a headline about a new particle. It may come from a paper whose most important sentence is just a number. Because in the end, this case is simple. A particle was weighed. The world does not agree on the weight. And until another experiment either confirms the heavy value or shuts the door on it, the W boson will sit right where it is now. Not solved, not dismissed. Just heavy enough to keep the standard model under pressure.